What's up, AP Physics C Mechanics students? Welcome back to our elegant physics video. Today's topic 5.3 rotational inertia, so let's jump right in. Let's start by defining the axis of rotation. Axis of rotation means the imaginary line around which an object turns. This imaginary line may pass through the object, such as through its center of mass. Here in the three cases, the axis of rotation is passing through the center of mass, and all the parts of the system or the object is rotating around this fixed axis. Also, it can be near its edge. So the axis of rotation, it passes through near of the edge. So still the axis of rotation belongs to the system or the object. Now here, as we can see, all the parts of the objects are rotating around fixed axis passes through the edge. Also, the axis of rotation, it may be located outside the object. So, for example, a satellite rotating around the Earth. The axis of rotation for the satellite passes through the Earth, the center of the Earth. So it doesn't belong to the object itself. It doesn't pass through the object itself. However, it's located outside the object. I mean the object, the satellite. When a system rotates about a fixed axis, every part of the system moves in circular path centered on that axis. Although different parts may have different distances from the axis of rotation, the farther apart is from the axis, the larger the circle it traces. So for example here, where the axis of rotation is passing through the edge of the object, if we consider a small tiny piece of this rod, such as this one here, it will trace this circular path during its rotation around the fixed axis. However, for another mass belong to this rod, and let's consider this mass here, it will trace a bigger circle during its rotation around this axis. Moment of inertia, particle-like object. As we are developing rotational mechanics formalism, the linear kinematics equations can be extended to rotational motion by replacing linear quantities such as velocity, position, displacement, acceleration with angular quantities such as angular position theta, angular displacement delta theta, angular velocity omega, and angular acceleration alpha. Now we need to promote the inertia in order to introduce different missing laws. And what I mean by inertia is the mass. In rotational dynamics, is not only about the quantity itself, but also related to the mass distribution about the axis of rotation. So previously in Unit 2, we have developed a big law known as the Newton's second law. In the Newton's second law, we have defined the mass or the inertia. Here in rotational kinematics or rotational dynamics, when we will start working with Newtonian mechanics, we need to promote or to modify the mass in order to take in consideration the distribution of the mass around the fixed axis. So let's consider an axis of rotation delta and an object of mass m1 at a distance x1 from the axis of rotation. So let's assume this is the axis of rotation and this is the mass m1 where it's located at the distance x1. Now this mass 1, it's rotating around this fixed axis, making this circular path. The object in a particle like the dimension, and I mean by the particle like, the dimension of the objects are negligible. We define the moment of inertia, or in other words, the resistance of the motion, or to the motion, to given by I is equal m1 x1 squared, where m is the mass of the object in kilogram and x is the distance between the object and the axis of rotation. Now I is known as the moment of inertia, and it has a unit of kilogram meter squared. Now because the mass is in kilogram, the x in meter, but since we have squared, it should be written as meter squared. As a result, the I will be measured in kilogram meter squared. m1 is the mass of the object in kilogram, x1 is the distance from the center of mass of the object to the axis of rotation in meter. The moment of inertia I is an additive quantity, which means if we have more than one mass forming a system, and these masses are rotating around the same fixed axis, then, such as this case, we have here 4 masses located at different distances from the axis of rotation, then the moment of inertia of the system is given by the summation of mi xi squared, which means we need to consider m1 x1 squared, m2 x squared, x2 squared, m3 x3 squared, m4 x4 squared, and so on. In other words, we're gonna add up all the moment of inertia together. So I1 plus I2 plus I3 and so on. Moment of inertia for extended object. To determine the moment of inertia I for an extended object, for example here the road, first the axis of rotation should be specified. And here let's assume that the axis of rotation is passing through the center of mass of the road. After that, we need to divide the object into differential masses, which means we're gonna split our object into small and tiny pieces. For example, dm1, dm2, dm3, up to infinity. The origin is the axis of rotation itself. So whenever we have specified the axis of rotation, we're gonna consider the origin to be exactly at the axis of rotation, or passes through the axis of rotation. So we draw the x-axis, such as this x-axis will make an intersection with the delta, the axis of rotation, at a point. This point will be the origin. Now, if the length of the road is L, then from here to here will be L over 2, and from here to here will be L over 2. So if we want to write the position of each of these 2 points, remember that the position is defined to be the distance with the direction from the origin. So the direction is to the right, which means it's plus, and the distance is L over 2. So this point is located at L over 2. And what about this point? This is on the left-hand side, which means it's going to be minus, and the distance will be L over 2. So this length actually is extended along a range between minus L over 2 to L over 2, where the length of this rod is L. And then the moment of inertia for a given extended object with respect to the axis of rotation delta is given by, we find the summation of every single small and tiny piece multiplied by its distance squared from the axis of rotation. So for example, we're going to consider this mass and the distance from the axis of rotation, and this mass here and here and here and there. So we will consider every single mass and its distance from the axis of rotation to find the total moment of inertia for this rod. As we divide a given object into more and more infinite differential masses, in the limit of producing the full extended object, the summation operator will be promoted to an integral. And we know that in calculus we can replace the summation into integration, and the moment of inertia for the extended object is given by I is equal integral the x squared dm from x initial to x final. And pay attention here, the variable will be the mass. The integral is a composite of variables, both position and mass. Both variables can be unified using density mass distribution. Now let me remind you, with the density mass distribution, it can be lambda, sigma, or rho. Now lambda is the linear mass density, sigma is the surface mass density, and rho is the volume mass density. And we know that the lambda is given by dm over dx. So sometimes, or most of the time, you're gonna find lambda written as a function of distance. So we can express dm in terms of lambda dx. Remarks, this method works for both mass distribution, whether the distribution is uniform or non-uniform. Always choose the origin to be the axis of rotation itself. Now, moment of inertia for some objects, for example, a hoop of mass m and radius r, where the axis of rotation passes through the center of the hoop, then the moment of inertia here in this case will be given by I is equal mr squared. Now, for a sphere with the mass m and the radius r, and where the axis of rotation passes through the center of the sphere, the moment of inertia will be written as I is equal to 2 over 5 mr squared. Now, if we change the axis of rotation, so we let the axis of rotation to be passes through a point located on the circumference of the sphere, then the moment of inertia will be given by I is equal 7 over 5 mr squared. And one can notice that the two relationships They are related to each other, and moreover, for this relation, for this moment of inertia, this moment of inertia is bigger than this one, because we know that 2 over 5 is less than 7 over 5. And this is true because we know that as the axis of rotation, or the mass is getting farther away from the axis of rotation, the moment of inertia will be bigger. Now, a rod of mass m and the length L, where the axis of rotation passes through exactly the center of the rod, the moment of inertia is given by 1 over 12 ml squared, where L is the length of the rod. And if we shift the axis of rotation toward the edge of the rod, then the moment of inertia will be given as I is equal 1 over 3 ml squared. Now we will see how we can transform the moment of inertia, or the expression of the moment of inertia, from this one to that one, and this can be done by the parallel axis theorem. Consider an object of uniform distribution and of mass m that can rotate about an axis, passes through the center of mass. Now, hence the resistance of motion, or the moment of inertia, let's call it I center of mass. Suppose that the axis of rotation has been shifted by a distance d from location of the center of mass. Now we have shifted the axis of rotation, let's say, to the left, to this location. This is the new axis of rotation, and the whole system will start be rotating around this fixed axis. Now the object rotates about in the new axis of rotation delta prime, that is a distance d from delta. In this case, the moment of inertia of the system changes from I center of mass to new moment of inertia given by I. Because the moment of inertia is not only about the mass, which remained unchanged, it's also rotated about how much the distance between the axis of rotation and the mass, or in other words, the mass and its distribution around the x-axis. However, both I and I center of mass can be related by using a very beautiful theorem known as the parallel axis theorem. And let's apply the parallel axis theorem now. The new moment of inertia will be given by the moment of inertia around the center of mass plus m times d squared. So plus the mass of the object times the distance between the old axis of rotation and the new axis of rotation. Now, knowing that the ICM is the moment of inertia of the rod when the delta, or the axis of rotation, passes through exactly the center of mass. I is the new moment of inertia around delta prime, and it's given by kilogram meter squared. ICM is the moment of inertia around delta passing through its center of mass, and m is the mass of the object in kilogram. D is the distance between delta and delta prime. So let's solve this question. Exercise 1. A 5 kilogram sphere is connected to a 10 kilogram sphere by a rigid rod of negligible mass. So from now on, whenever we have negligible mass, or whenever the mass is neglected, then we can ignore the moment of inertia of the negligible mass. So for example here, since the rod has negligible mass, so it has no moment of inertia. Only the moment of inertia will be associated with the object with mass. So in this case, the 5 kilogram will have a moment of inertia as well as the 10 kilogram. The sphere rod combination can be pivoted about an axis that is perpendicular to the plane of the page, and that passes through one of the 5 lettered points. So it can pass through E, D, C, B, or even A. Through which point should the axis pass for the moment of inertia of the sphere rod combination about the axis, or this axis, to be the greatest? So here we are looking for a point such that this point, if the axis of rotation is passing through it, it will make the total moment of inertia of the system the greatest. So for a given mass, to make I as large as possible, the mass should be as far as possible from the axis of rotation. Because according to the formula, I is equal mr squared. So for a given mass, as the r increases, the moment of inertia increases. Now, for a system of masses, to get the maximum moment of inertia, we place the heavier object at the greatest distance from the axis of rotation. So now, which one of these two masses is the greatest mass? So we know that the 10 kilogram is the greatest. So we place it such that it's at very, very far distance from the axis of rotation. Now we cannot control the mass is fixed here, but we can control at which point we should pass our axis of rotation. The farthest distance from the A, the bigger the total moment of inertia. So the farthest point will be exactly at E, because A is the heavier mass. So to get the larger possible I, we let our axis of rotation to be passed through E, and the correct answer will be E. A solid disk of mass capital M and radius R is freely rotating horizontally in counterclockwise. So this is the direction of the rotation of the disk. The angular speed is omega about a vertical axis through its center with negligible friction. As we can see here, the axis of rotation is passing through the center of the first disk. The rotational inertia, or the moment of inertia of the first disk, is mr squared over r. mr squared over 2. A second identical disk is at rest and suspended above the first disk with the centers of the two disks aligned, as shown in the figure above. There is no contact between the disks, and the second disk is dropped into the first disk. And after a short time, they rotate counterclockwise with the same angular speed omega final. So here what will happen, we drop this disk down, so both of them will now are forming one body, and the total linear, or the total moment of inertia of such like this system is gonna be the combination of I1 from the first disk and the I2 from the second disk of the second disk. Now since they are identical, then they will have the same moment of inertia. The moment of inertia for the first body is mr squared over 2, and for the second body it's gonna be the same moment of inertia. As a result, the moment of inertia will be given by I is equal mr squared. This is the total moment of inertia of the two bodies. The two disks are now shifted so that the axis of rotation goes through a point on the edge of the disk. The rotational inertia of the two disk system is now. So what did we do here? We have shifted the axis of rotation to be exactly in this place. We know that whenever we shift the moment of inertia to find the new, or whenever we have moved the axis of rotation, the new moment of inertia can be calculated or can be found using the parallel axis theorem. So the parallel axis theorem states that the new moment of inertia is the moment of inertia Cm plus md squared. Now where I is the moment of inertia, ICM is the moment of inertia when the axis of rotation was passing through the center of mass, and this is the moment of inertia in that case. M is the total mass of the disk. So actually here the total mass of the disk will be 2m, and d is the distance between the axis of the delta, which is the axis of rotation through the center of mass, and delta prime, the axis of rotation at the edge, and the distance from here to there is simply r. So the final answer, 2mr squared plus mr squared, is going to be 3mr squared, and the correct answer is B. Exercise 3. The uniform thin rod shown above has mass m and length L. The moment of inertia of the rod about an axis through its center and perpendicular to the rod is 1 over 12 ml squared. What is the moment of inertia of the rod about an axis perpendicular to the rod and passing through point P? So we have changed the point where the axis of rotation is passing through it. Now it has been shifted to B. It was located here through the center of mass. Now it's passing through a new point P, which is halfway between the center and the end of the rod. So exactly here. Now if the rod has a length of L, then from the center to the edge is L over 2, and from the center to the other edge is L over 2. Now L over 2, since P is located in the halfway, half of L over 2 will be L over 4 here and L over 4 there. And why did I calculate it in this way? Because I need to know what is the distance between the old axis of rotation and the new axis of rotation. because whenever we have shifted the axis of rotation, to find the new moment of inertia, we need to apply the parallel axis theorem. So the new moment of inertia is equal the old, which is the one that passes through the center of mass, plus the mass of the rod, which is here m, times the distance between them, d squared, between the two axes. Now the moment of inertia when the axis of rotation is passing through the center of mass, it was 1/12 ml squared. Now the mass is the same. However, now the distance between the old axis of rotation and the new axis of rotation is L/4 to the power 2. And it's equal to 1/12 ml squared plus ml squared over 16. So the square for L and for 4. We can take ml squared as a common factor, and we will end with 1/12 plus 1/16. Now plugging this in the calculator, and the final answer is 7/48 ml squared. So the correct answer is actually E. A rod with a non-uniform mass density given by, now from this relationship we have the density in terms of position, which means the density is not the same for different points. As the x increases, the density of the mass will increases, and this is shown here in the figure. As you can see, this part is darker than this part, which means that the mass here, the density of the mass here is much greater than the density of the mass there. However, we cannot rely on the sketch itself, because we need to analyze the equation itself. And yes, the equation states that as the x increases, the density will increase as well. Now A is 5 kilogram meter to the power 3, is aligned on the x-axis with one end and at the origin, and the other end is at 2 meters. So one can say that the length of the rod is 2 meters. The rotational inertia of the rod about the origin is most nearly. Now this case is extended object, so to find the inertia we need to rely on the integration x initial, x final, x squared dm. Now dm can be expressed as lambda dx, so it is equal to x initial, x final, x squared lambda dx. Now lambda itself is written as ax squared Now a is a constant, so we can place it away from the integration. Now x squared times x squared is x to the power 4. What about the boundaries? What is the x initial? The x initial is 0. This is the x initial. And the x final, because we need all the rod, we need to find the moment of inertia of the rod, so we're gonna extend our integration from 0 to cover the whole length, which is, in this case, the other extremity is located as x final, 2 meters. So we just can say that our boundaries are from 0 to 2. Now a is given by 5. What is the integration of x to the power 4? We know that the integration will be, we increase the power by 1, we divide over the new power. So x to the power 5 over 5 from 0 to 2. So 5, we substitute 2 here. 2 to the power 5 over 5 minus 0 to the power 5 over 5. Now this becomes 0. 5 with 5 cancelled out. We just need to evaluate to 2 to the power 5, and 2 to the power 5 is 32 kilogram meter to the power 2. This is the new moment of inertia, or this is the moment of inertia. The rotational inertia of a slim rod of mass m and the length L about perpendicular axis through its center of mass ml squared over 12. What is the rotational inertia of the rod about perpendicular axis through a point on the rod at a distance of L over 3 from the center of mass of the rod? Now previously, when was the axis of rotation passes through the center of mass, the inertia was ml squared over 12. Now we have shifted the axis of rotation to be exactly at the distance L over 3 from the old axis of rotation. So the distance between the delta and the delta prime is L over 3. How we can find the new moment of inertia? In this case, whenever we have shifted the axis of rotation, then we use the parallel axis theorem to find the new moment of inertia. And the new moment of inertia is given by ICM plus the mass d squared, where d is the distance between the two axes. Now, the center of mass, the moment of inertia through the center of mass, ml squared over 12. Now, m represents the mass of the rod, and the mass of the rod is the same, it's m. And d is the distance between the two axes, so it's going to be L over 3 to the power 2. Now, we apply the square here, so ml squared over 12 plus ml squared over 3. We take ml squared as a common factor, so 1 over 12 plus 1 over 3. So the final answer is 7 over 36 ml squared. And B is the correct answer. The rotational inertia of a sphere of mass capital M and radius r about a diameter is 2 over 5 mr squared. So this moment of inertia when the axis of rotation is passing through the diameter, and when I say diameter, I mean by that the center of mass, because the diameter is passing through the center of mass. So since the axis is aligned with the diameter, then the axis of rotation is passing through the center of mass. The rotational inertia about an axis tangent to the sphere. So what will happen to the moment of inertia if we shifted the axis of rotation to be tangent to the sphere? So we have moved it at the distance r. Since from the center to the edge, the distance will be equal to the radius, and the radius here is capital R. Again, whenever we have shifted the axis of rotation, then parallel axis theorem will help me to find the new moment of inertia, and it's written as I center of mass plus md squared. The I center of mass is given by 2 over 5 mr squared, and the mass is the mass of the sphere. The distance between the old axis of rotation and the new axis of rotation is r squared. So by taking mr squared as a common factor, 2 over 5 plus 1, so the answer is 7 over 5 mr squared is the new moment of inertia. So the correct answer is B. That's it for today's lesson. Thank you for joining me, and see you in the next video soon.